Hello everyone, my name is Schutski. I'm a research scientist at Skoltech, and today I'm going to present an overview of graphical models for tensor network contraction and other tasks. Why graphical models? Machine learning is a science about distributions. We can try to represent them with lengthy and sometimes ugly formulas, but I believe that graphical models provide much better and intuitive way. Also, this section is about graphs, and I will have lots of graphs in my talk. An additional benefit of graphical models is that the notation similar to graphical models is quite popular across different fields of science, and you can build intuitions in all of these fields. Finally, not even graphical models are a representation, but also they're a tool which helps you to relate statistics to complexity theory, for example, and to study different properties of the distribution. Okay, so first I have to note that this is my very own view of the topic based on 2 years of experience with graphical models. I will base my story on this great review article cited below, which is not very popular, but I think it's very clear and deserves your attention. We'll start with the definition of graphical models. Then I will introduce a very general, and I would say the main algorithm for graphical models called variable elimination. Then I will show that variable elimination is related to tree decompositions and that you can estimate the complexity of variable elimination using tree decompositions. Then we will touch upon message passing algorithms, and finally I will introduce some of our recent results in parallel elimination of graphical models. Suppose you are studying a joint distribution of discrete random variables for simplicity. For example, each of these variables can be a result of some medical test, and you are trying to model whether there is a disease or not. Some of these variables can be correlated with each other, which is expressed by the potential functions psi acting on groups of correlated variables. The joint probability distribution is then a product of these potential functions divided by a normalizing constant, which is a sum over all possible configurations of the variables. These types of models are known as Markov random fields or Bayesian networks. In Markov random fields, the potentials may not be normalized. And to write down an exact joint distribution, you need to evaluate this constant z, which is called partition function in physics. Markov random fields are widely used in physics, and for example, an Ising model is a Markov random field. Another type of models are Bayesian networks, which are generally used in statistics, and in Bayesian networks, these potential functions psi are exactly normalized conditional probabilities. To represent this joint probability, you can use a graph where every vertex corresponds to a variable and edges correspond to potential functions. If the potential functions acts on a pair of variables, then it corresponds to an edge. And if a potential function acts on some bigger group of variables, then it corresponds to a connected subgraph or a clique in the graphical model. I have to note that even neural networks can be treated as graphical models if you introduce nonlinear activation functions over groups of variables. A very good introduction into graphical models and different algorithms on them is this book of Kohler and Friedman, Probabilistic Graphical Models, Principles and Techniques. Another popular graphical notation are tensor networks. Tensor networks originated in physics, where they are used to represent density matrices and wave functions. Later, they were adapted in other fields like numerical linear algebra to solve differential equations, or in machine learning to compress neural networks. You almost certainly encountered them in some other situations. For example, if you ever try to evaluate some expression with numpy einsum, you are constructing a tensor network. As an example, consider this contraction of a set of tensors shown above. It can be expressed graphically with a tensor network as follows. Every tensor is a vertex and every index is a leg coming out of this vertex. For example, there is an example of a vector A, and it has a single index I, and the matrix F, which has two indices L and M. Connected indices are summed over, so on the right, this diagram represents a product of two matrices F and J. A very good overview of tensor networks is a book of Andrzej Schutski, Tensor Networks for Dimensionality Reduction and Large-Scale Optimization. It turns out that tensor networks are line graphs of graphical models, which means that if you replace all edges in a tensor network by vertices and all vertices by cliques, then you get a graphical model. Here on the left, there is an example of a tensor network, and look at the tensor B, which has three indices I, J, and K. And on the right, it is represented by a clique in a graphical model, also called B, on vertices I, J, and K. An advantage of graphical models over tensor networks is that they can represent contractions over indices shared by more than two tensors. In case of tensor networks, a proper way to draw that would be to use hypergraphs, or graphs where edges can be shared by more than two vertices. Or to introduce these dots, as I did here on the left, but this is not quite standard. You may think, why should you bother to learn more about tensor networks as a machine learning researcher? Well, because if people someday are going to build quantum computers to do quantum machine learning, then all programs will be implemented as quantum circuits. Quantum circuits are tensor networks with some complex valued tensors, and usually these are just small matrices with fixed entries. And these tensor networks are implemented in hardware on chip, so running a quantum program is equivalent to the evaluation of tensor network contraction. Quantum circuits are like complex valued neural networks without activation functions. Of course, they can be simulated and studied with graphical models equivalently, and I would recommend you to look up these two works below, which use graphical models to simulate quantum circuits. Another class of problems which can be solved with graphical models are constraint satisfaction problems. As an example, suppose you have a set of Boolean variables and you would like to find an assignment of these variables such that some expression like the one shown above evaluates to true. This is a famous satisfiability problem, or simply SAT. SAT was the first problem used to formulate what it means to be NP-complete for a problem. NP-completeness means that the number of resources you need to find an exact solution of this problem is exponential in the size of the input. So for SAT, the number of comparisons or runtime will be exponential in the number of variables and the number of clauses. Many problems in graph theory are proven to be NP-complete by transforming them into an instance of SAT or some other NP problem. Here on the left is shown a reduction offset to a click problem on graphs. A click problem is finding a maximal click in a graph. And you may notice that this graph already looks very much like a graphical model. I would like also to recommend this book of Kronig and Strichman for a very good introduction into constraint satisfaction problems. It turns out that it is possible to write potential functions such that a graphical model encodes a constraint satisfaction problem. A general constraint satisfaction problem is a generalization of satisfiability where some of the conditions in parentheses can be violated, which means that these are soft constraints. Each of the soft constraints has a corresponding integer weight attached to it. And then the goal is to minimize the sum of these integer weights. The potential functions in constraint satisfaction problems will then take an infinity value for hard constraints and some integer value for soft constraints. These networks can be easily transformed into usual Markov random fields by applying exponentiation to their potential functions. And then solving a constraint satisfaction problem will be equivalent to finding the most probable configuration or mode of the Markov random field. Below is a reference to a very good book of Rossi on constraint programming. Here is a summary of some algorithms which can be formulated as graphical models. Roughly, they split into two groups. The first group represents algorithms which produce a full or partial sum of a graphical model. In statistics, this is a marginalization task where we take a sum over some subset of variables to calculate marginal probability distributions. Another task is to find the most probable assignment of the graphical model. Some algorithms like Viterbi decoding do exactly that. It is quite interesting though that there is one procedure which generalizes both of these tasks and has all of these applications. This general procedure is called variable elimination, and it comprises two steps. First is an aggregation step, where for a selected variable in the graphical model, we collect all the potentials which contain this variable and combine them into a single large potential. In the graph language, it means that we introduce a click over all of the neighbors of this selected variable. If each variable can take up to L values, then we'll need L to the power of the number of neighbors multiplications to perform this operation. Another step of the algorithm is a reduction step, where we remove a selected variable from the graph by summing over its values or taking a maximum. To do that, we need L to the power of the number of neighbors plus 1 operations. Both partial summation of a graphical model and optimization task can be solved with variable elimination algorithm. In optimization problem, the only addition is that we need to keep the index of the maximizing value of variables at each reduction step. In the table below are the examples of the combination and reduction operators for different tasks. Let's work through an example of tensor network contraction. We take the same expression as before, and our goal is to evaluate the sum over all indices in this expression. On the right, we drew graphs corresponding to each step in the contraction sequence. Here loops mean vectors like AI, edges mean matrices like H, hj, and cliques are tensors like b, ijk. As we sum over indices, they are removed from the graph one by one, and cliques are introduced over their neighbors. These cliques correspond to intermediates in the contraction sequence, and it is also easy to find an exact number of multiplications and summations in each step. This number equals L to the power of the number of neighbors plus 1 at every step. It turns out that the order of contractions influences the complexity of the overall algorithm. If we contract indices in order h, I, j, k, then the maximal dimension of the intermediate is 3, and the overall cost will be L to the power 4. But if we do it in order h, k, I, j, then we'll encounter an intermediate of the dimension 4, and the overall cost will be L to the 5th power. The complexity of different orders can differ exponentially, and the question is that how to find orders such that the variable elimination has the lowest cost. To formulate this problem in terms of graphs, let me show that any ordering of vertices maps a graph into a tree. The vertices in this tree are cliques in the original graph, which emerged during some elimination sequence. Here is an example of how to build this tree graph. Suppose we first eliminate a vertex h. This procedure produces a clique hj, and we add this vertex, called a back, into a tree. Then we eliminate I. I has neighbors jk, so we add another back ijk to the tree. Then we add a clique jkl. jkl shares vertices with previous cliques, so it should be connected to them. We should proceed in this way until all vertices of the initial graph are contained in some vertices or backs of the tree. You can find a version of this algorithm with longer explanation in our work, cited below. The resulting map of a graph into a tree is called tree decomposition of this graph, and the number of elements in the maximal node of the tree minus 1 is called treewidth. Treewidth measures the similarity of the graph with the tree. For example, treewidth of trees is 1. A more formal definition of tree decomposition is as follows. Tree decomposition is a map between two graphs such that every vertex of the original graph G is contained in some back or vertex of the tree graph F. Also, if there is an edge between two vertices in G, then there is a back such that both of these vertices are contained in it. And finally, each vertex of the initial graph induces a subtree in the tree graph. For example, on the image on the left, G, the vertex G, induces a subtree in the tree graph. Tree decomposition was introduced by Robertson and Seymour, and they showed that it characterizes the structure of the graph. If treewidth is large, then the graph has to contain some large minors. A famous review of tree decomposition is an article of Hans Bodlander. And also an explanational picture on the left shows that backs in the tree decompositions are exactly cliques. Intersections of these backs are separators in the graph, and separator is a set of vertices which you can remove, and then the graph becomes disconnected. and the treewidth is also the size of the largest bag minus 1. Some facts about tree decomposition. Finding tree decomposition of minimal width is NP-complete, and this means that finding an optimal elimination order is also NP-complete. Multiple orders may correspond to the same tree. However, it is easy to extract some order from a given tree. The intersections of bugs in the tree are separators of the initial graph, as I mentioned, and this later fact gives rise to modern algorithms for searching minimal tree decompositions. Currently, the fastest algorithms for tree decomposition are presented in these two works cited on the bottom right. Usually when people hear that a problem is NP-complete, they may think that solving these problems may take very large amount of time and resources, and that problem is not solvable in general. In practice, it turns out that good solutions can be obtained quite efficiently, and you need a lot of time to find a global minimum, which may be not much better than an approximate solution. After obtaining a tree decomposition with minimal width, we can do variable elimination on the resulting tree instead of the initial graph. The optimal elimination order on trees is to recursively eliminate leaf vertices. This corresponds to the elimination of blocks of variables in the initial graph. In block elimination, at each step, we remove vertices which are in the current bag in the tree and are not shared by its neighbors. So these vertices are not in the separator at the current step. We can exactly determine computational and space requirements from the tree decomposition without even performing any calculations and actually without running variable elimination. So the tree decomposition helps to measure complexity of graphical models. Okay, that was variable elimination, which is an exact algorithm to marginalize graphical models. There is another approach which generalizes variable elimination called belief propagation, message passing, or forward-backward algorithm. Message passing got lots of attention recently in the study of the expressive power of graph neural networks because of its relation to the graph isomorphism test. How does belief propagation work? Suppose you have a tree graphical model, which means that the potentials can act either on a single variable or on a pair of variables. The goal is to obtain marginals for every variable in the model. As the model is a tree, we can choose an arbitrary root and orient every edge towards this root, as is done on the upper left figure. Then we run a two-step algorithm. First, we recursively calculate a message vector for each node starting from leaves. Messages are partial sums of the potentials over the children of the current vertex. For example, for vertex 3, the sum will run over the variables 4 and 5, but not the variable 2. After all vertices are processed this way, at the second step, the updates are performed in reverse order, so the parent-child relation is reversed. We update the messages with the sum of local potentials at the current vertex times the messages of the children of this vertex. The messages are then normalized by their L1 norm to ensure they have a meaning of probability and to ensure convergence. The forward-backward algorithm is exact on trees. After these two steps, messages are exactly marginals of their variables. Also, I would like to point that backpropagation in neural networks is actually a forward-backward algorithm and is very similar to this belief propagation algorithm. So what happens if the same procedure is applied to general graphs? Well, then there is no guarantee that in two steps messages will converge. Still, in practice, often this is the case, and general graphical models can be marginalized in this way. Lots of research went into the questions of the convergence and errors of approximate belief propagation, but still I would say there is no definitive answer when it works and how large the errors may be. Another approach is to take a graph and turn it into a tree with the help of tree decomposition, as we did before, and to run belief propagation over blocks. But then the cost of this belief propagation will equal to the cost of variable elimination. It is interesting to note also that belief propagation can be used to parameterize graphical models. So after we obtained marginal distributions over the variables, we can merge these probabilities into the potentials, and we can obtain other graphical model with more localized potentials, for example. Finally, I would like to overview our recent work on parallel evaluation of graphical models. Suppose that you are interested in some specific configuration of a subset of variables. This happens when you deal with conditional distributions, or during the decoding of error correction codes, or when you are evaluating some specific slice of a tensor network using graphical models. So in this example, suppose we are interested in the conditional distribution when we fix a variable k to value 2. All potentials are then sliced accordingly. In terms of graphs, this operation corresponds to the removal of the vertex of the fixed variable. Note that for any value of the variable k in its range, the resulting expressions are independent of each other and hence can be evaluated in parallel. The total sum of the graphical model is the sum of these partial expressions. This slicing is the idea behind parallel evaluation of graphical models. We can select some subset of m variables, fix their values, and this will produce m to the power l independent subtasks. However, different choice of these sliced variables will produce subtasks of different complexity. For example, if we parallelize over variable k, as was done before, then the graphical model of the subtask will have treewidth 1, as it is a tree. But if we parallelize over variable I, then the resulting graph will have treewidth 2. So the subtasks will be harder to evaluate. In general, it is NP hard to select vertices such that after their removal the graph will have minimal treewidths. In our work, we compare different heuristics for this task and proposed a new one which works really well. We get an improvement of 3 to 4 orders of magnitude in total computational time with this approach. For full details, I recommend you to see the paper, but I will explain the idea behind this method briefly in the next slide. This is the idea of our article. Let's take the graphical model from our example. If you are running variable elimination, then first you need to select the order of variables to eliminate. As we have seen, selection of the order is equivalent to some tree decomposition. Now let's recall a property of tree decompositions. Every variable of the original graph has a connected subtree in the tree graph. And hence the tree is just a sum of subtrees of individual variables. We can then pick variables which contribute to the largest number of the largest bags in the tree decomposition. And basically this is the idea of the heuristic. Okay, that was it, and I hope I demonstrated lots of interesting aspects of how graphical models can be used in probabilistic modeling and other fields. So here is a list of topics we went through and some references in case you want to go deeper. With that, I thank you, and I would be happy to answer your questions at the DataFest.